the machine that builds a railway across the sea. From the shore, it looks like a train has escaped its tracks and driven straight into the ocean. A long steel platform rests on pontoons. Tall legs descend into the seabed. Cranes move rail sections above the waves while hydraulic machinery inches the entire structure forward. It is not a ship, not a bridge, and not an ordinary construction train. It is a temporary offshore factory, a machine designed to create a precise railway-shaped worksite where there was only moving water. That sounds absurd, because railways depend on the one thing the sea refuses to provide, a stable reference. On land, surveyors can mark a line and machines can return to the same point every day. Offshore, wind pushes the hull sideways, waves lifted vertically, currents twisted around its anchor points, and the seabed may be soft enough to swallow heavy equipment. A deviation of only a few centimeters can turn a carefully aligned structure into a chain of accumulated errors. The real engineering challenge is therefore not simply carrying rails over water. It is making the water behave, temporarily, like solid ground. The machine begins as a modular floating platform. Instead of building one enormous custom vessel, engineers connect buoyant pontoons into a working deck. Each module contributes displacement, and the combined buoyancy supports cranes, hydraulic power packs, rail magazines, workshops, fuel, and crew spaces. Modular construction also changes the economics. Sections can be transported separately, assembled near the project, rearranged for a different load, and removed when the job is finished. But modularity creates its own problem. Every joint must transfer bending and torsional loads while the sea tries to make neighboring pontoons move independently. To control that motion, the platform uses a positioning system built from legs, spuds, anchors, or combinations of all three. A spud is a vertical steel member lowered through the platform into the seabed. Once several spuds engage, the floating deck can no longer drift freely. Hydraulic cylinders then preload the supports, testing whether the soil can carry the expected forces. On firmer ground, the platform becomes a temporary pier. In deeper or softer water, anchors and winches maintain position while motion sensors continuously measure heave, pitch, roll, and yaw. The goal is not perfect stillness. The goal is to reduce movement until construction tolerances become manageable. Now the railway part begins. The machine carries prefabricated elements in a deliberate sequence. A crane lifts a pile or support frame from the deck and rotates it over the working edge. Survey instruments compare the suspended component with a digital alignment model. Operators correct lateral position, heading, and elevation before lowering it. A vibratory hammer or hydraulic press drives the foundation into the seabed. Then another module follows, a crosshead, bearing seat, beam, or rail panel. Each installed piece becomes the reference for the next, so every measurement must include both local accuracy and the accumulated geometry of the entire line. This is why the machine resembles a locomotive. It advances along the path it is creating. Behind it, completed supports form a controlled corridor.
Steady, aligned with the
Ahead of it, open water remains an uncertain construction zone. The platform can pull itself forward with winches, shift along temporary rails, or leapfrog its spuds. One support remains fixed while another is raised and moved.
Watch the cable!
The motion is slow, often measured in meters per cycle, but it transforms a chaotic marine environment into a repeating industrial process. Stabilize. Survey. Lift. Align.
Frame lowering, watch the cable!
Install.
Steady, aligned with the
Verify.
bearings!
Advance. The most dangerous loads often appear between those verbs. A suspended beam behaves like a pendulum when the deck rolls. A crane load that is safe on land can generate violent dynamic forces offshore.
With the bearings.
Engineers therefore use motion limits, weather windows, taglines, active heave compensation, and strict stop criteria. If wave height, wind speed, or platform acceleration exceeds a threshold, the lift pauses. This can feel frustrating when the equipment is ready and the schedule is tight, but offshore construction rewards patience. A single uncontrolled swing can damage the component, overload the crane, or injure the crew. The seabed adds another layer of uncertainty. It may contain soft clay, dense sand, buried rock, old cables, pipelines, or debris. Before construction, survey vessels map the route with sonar and geotechnical borings. Even then, local conditions can surprise the installation team. A pile may refuse early because it hits a hard layer. Another may sink farther than predicted in weak soil. The machine must carry contingency tools, alternate driving heads, drilling equipment, grout systems, cutting tools, and spare components. What looks like one specialized machine is really a mobile collection of solutions to problems that have not happened yet. Power and control are distributed across the platform. Diesel generators or shore connections feed hydraulic pumps, cranes, winches, welding equipment, lighting, navigation electronics, and accommodation systems. A central control room combines position data, weather instruments, load cells, camera feeds, and crane telemetry. Operators do not simply command motion, they manage limits. Software can warn that a planned lift would exceed deck capacity in one orientation, that a spud load is rising unevenly, or that the next advance would place the platform outside its safe working envelope. The temporary railway itself may serve several purposes. It can carry materials for a bridge or causeway. It can support conveyors, pipelines, launch equipment, or maintenance vehicles. In coastal industry, a narrow rail corridor can move heavy modules farther and more predictably than road vehicles on weak reclaimed ground. In remote regions, the structure may exist only long enough to construct something permanent. The strange machine is valuable precisely because it does not need the final infrastructure to exist before work begins. It brings its own access route and extends that route one section at a time. Environmental constraints shape the design as strongly as structural loads. Turbidity curtains may contain disturbed sediment. Noise limits can change pile driving methods to protect marine life. Work
Position
seasons
confirmed
may
on
avoid
grid.
migration or
Feed
breeding
shows alignment.
periods.
Telemetry stable.
Fuel systems need secondary containment, and every loose object on deck must be secured against wind and waves. The platform must also leave as little behind as possible when the project ends.
Position
Temporary
confirmed on
piles
grid.
may be extracted,
Feed shows alignment.
modular pontoons
Telemetry stable.
disconnected, and the marine corridor restored. A successful machine is not only powerful enough to build offshore. It is controlled enough to disappear afterward. Consider the precision
Position
hidden
confirmed on
inside
grid.
one advanced cycle.
Feed shows alignment. Telemetry
First,
stable.
the crew confirms weather and equipment status. The active spuds or anchors are loaded and checked. Survey targets establish the machine's exact position. The next foundation
Position
point is
confirmed on
projected
grid.
into the real
Feed
world.
shows alignment.
A
Telemetry
crane
stable.
transfers the component while sensors track load and motion. Installation equipment drives or seats it. Surveyors measure the result. If the error is acceptable, the geometry model updates. Only then does the machine release a support and move forward. Hundreds of measurements and safety decisions are compressed into a few visible meters of progress. That is the hidden logic behind the offshore locomotive. Its unusual shape is not an attempt to make a train float. It is the consequence of combining four incompatible demands. It must be buoyant enough to reach the site, rigid enough to carry precision equipment, anchored enough to resist the sea, and mobile enough to advance without an existing road. Every pontoon, spud, winch, crane, and sensor answers one part of that contradiction. Machines like this reveal a broader truth about engineering. The most remarkable designs are rarely strange for the sake of being strange. They look impossible because the problem forces familiar systems to merge. A vessel becomes a factory. a platform becomes a temporary island. A crane becomes part of a positioning system. And a railway construction machine becomes its own moving foundation. The next time a line of steel appears to cross open water, look beyond the finished structure. Somewhere at its leading edge, there may be a machine advancing one careful cycle at a time, carrying solid ground with it. It does not defeat the ocean. It measures the ocean, braces against it, waits for the right moment, and turns uncertainty into a repeatable process. That is how a railway can begin where the land ends.